So, again, welcome to lecture 13. So we'll continue on from where we were before. So, to begin the lecture, let me just write down a theorem. So maybe I'll just recall what we had. So, so we have A, which is an adapted boundary operator, and we have the model operator with respect to this, which is this on the cylinder, right? So this is the setup. Oh, sorry, it's partial M. Okay, and so let's write down a theorem now. So the theorem is that, so the check space of this operator D naught is precisely equal to the space that we wrote down with respect to this A. Okay, so we can now decompose this as chi minus acting on, so this is equal to, so when I say equality here, I mean really equality as Banach spaces, right? So it means the norms on each of these spaces are equivalent. Let's just recall what this is. Okay, so that's the theorem. So this is the first important theorem that connects all that we've been talking about in terms of all these boundary value problems with the analysis that we've done of the adapted operator on the boundary. Okay, so this is really a description of the operator D naught, the interior problem with respect to an operator on the boundary. Okay, so we'll take this further in time to come, but so far this is what we'll prove. Okay, so what's the proof? So the first thing we want to prove is that H check of D is contained in H check A of D. So let's take U in DOM D naught max. Okay, so then there exists some compactly supported smooth sections such that UN converges to U in the D naught max norm, right? So this completeness of the operator D naught comes from the fact that we're on the cylinder, okay? On the infinite cylinder. So, yes, there are D zeros everywhere. Yes. Okay, so what is lemma? So last time we saw two lemmas, right? We proved two lemmas. So from a lemma from last time, from previous lemma, what can we say? So we can say that UN restricted to the boundary minus UM restricted to the boundary. So we have this estimate, right? H check A D naught. This is bounded by UN minus UM in the D naught M norm. Okay? So we know that, so in particular we know that because this converges to U, that this sequence is Cauchy. So because this sequence is Cauchy, it means that we have the trace map is well defined, so this is exactly equal to the limit as n tends to infinity of UN restricted to the boundary. And in particular, we have the following, right? So we have U, so we have that the, I mean, this trivially follows. So this estimate, so this is going to be the limit as n tends to infinity of UN restricted to the boundary h check a of d naught, and trivially this is going to be bounded by, I'll write it here, as we said just now. So this is bounded by un d naught max, or d naught I should say. It's just the graph norm. And so this is obviously equal to u of d naught. Okay, so we've shown that the trace, so this shows that the trace is well defined, and then it shows that actually the trace is continuous into this space, okay, with respect to the d naught topology and with respect to the topology on h check a. And so in particular, this shows also that what we want, right? That h check of d naught as a set is contained in h check a of d naught. Okay, so the other direction, so now for h a check d naught is contained in h check of d naught. So for this, we use also the other lemma, right? So let W be in h check a of d naught. And so we have E of the extension operator applied to W from the previous lemma is in dom d naught max. So this is previous lemma. And also we have EW restricted to the boundary now is equal to W. So this shows the opposite containment. Okay? So we know a priori, we know that U maps, the kernel of U maps to U restricted is equal to dom d0 min. So what have we got? So we've shown that U restricted to U partial m from dom d0 max to this space h check of a d naught is a bounded surjection with kernel U restricted to m equal to h is equal to dom d naught min. So that means that h check of a d naught is isomorphic, but in particular it's equal, right? So it's equal to this h check space with comparable norms. Okay, so that's the proof. I want to just also note something else here. If A is any boundary adapted operator, and Rj is a spectral cut, or R is a spectral cut, i.e. A minus R, so A equals AR equals A minus R is omega is bisectorial and invertible, then letting d naught equals sigma naught dt, well, this is what we define it to be, and dr equal to d naught dt plus ar, we have h check of dr is equal to h check of d naught, which is equal to exactly this ar. Well, okay, so it's maybe d naught dr is h check of ar dr. Okay, so why is this true? Well, it's actually very easy, right? Or we have to, I mean, here we've done nothing but just perturb our original operator by a constant. So suffices to note that the graph norm of dr, which is u plus dr of u, is now comparable, the squares, to d naught of u. Right? So this is just because we've just added some constant r, so it gets absorbed into the lower order term. So in particular, the maximal domains are equal, and then we can just move one problem to the other. Okay, so all of the stuff that we've just done follows trivially. Okay, so let me now just make a very quick remark. So in the literature, people often talk about Calderon projectors, and this is just really a side remark because this is not so important for us, but I should make this remark. So in fact, it is not difficult to show that chi plus of a, so this is again back in the situation where we are invertible omega bisectorial, right? Or yeah, h minus a half is actually equal to the trace map, so gamma, acting on the kernel of d max, d naught max. Okay, so the key point though, the real key point here is, we have described this in terms of an operator on the boundary. Okay, so later on we want to show that we can take we can always deform the maximal domain near the boundary so that we can end up in this scenario, right? That's what we'll see as we go along. But the point is that this object chi plus h minus a half is not a mysterious object. It's actually the Calderon projector, or it's the range of a Calderon projector with respect to this model operator d naught. Okay. So let's push on a little bit more, because we now have the check space, and now we want to also understand how to relate adjoint, the formal adjoint of this operator, and also adjoint boundary conditions, right? So so obviously we want some sort of Green's formula here. So recall that d naught uv minus u d naught, well, that's not what I wanted to write. Let's compute this, right? So sigma naught dt plus a uv. So this is for u in compactly supported things on the interior, not touching the boundary. V is in C infinity cc of f, zf. So now I'm going to pull across, and then I pull everything across here. So what I get here now is negative dt plus a adjoint sigma naught star of v. Okay, but now I'm going to factor out this part here, right? So I'm going to have sigma naught star, and I'm going to introduce a minus sign here because I want this to be dt plus. So now I get a negative sign here, so I get star inverse a star acting on v. Okay, so i.e. So we see that d dagger of naught is equal to precisely sigma naught star dt minus sigma naught star inverse a star sigma naught star, and therefore the induced adapted boundary operator for d naught perp from A is, well, I'm gonna now define this as a tilde. So for the moment, when we're talking about this, let's talk about this a tilde. So this is negative of this thing inverse a star sigma naught star. Okay, so this is the adapted operator. The induced adapted operator for the formal adjoint from A. Also note that I'm being a bit naughty here. I mean, this is really the formal adjoint, right? Because we're really talking about differential operators. But again, the remark here is that we are talking about the non-closed operator acting on compactly supported or smooth functions, and also we're talking about its closure, which is unique because we're now on the boundary. And the boundary is a boundaryless operator. Okay, the boundary is a boundaryless manifold, so everything is uniquely determined. Okay, so lemma. Over the boundary, sigma naught inverse star, which is a map from, which is a bundle, which is a map from E to F, induces an isomorphism from H hat A of D naught to H check A tilde of D naught formal adjoint, where A tilde is the induced adapted operator for D naught bar from A. Yes, always. We have, so the question is the adjoint of the inverse of the adjoint? Yes. And this was an exercise in some time back. Yes. Okay, the pairing beta uv defined as negative sigma naught u v L2 on the boundary in F for u in C infinity C, so I don't have to have C infinity C there because I'm on the boundary, so this is for U, and V in F extends to a reflexive perfect pairing between these spaces. So actually the statement should be the other way around, right? We have the perfect pairing, it's reflexive, and therefore this this space has to be isomorphic to the adjoint of this space, which we know is the hat space, right? So that's how it goes. Okay, so let's prove this. We already have that, so this is something we've already proved, right? That H hat A of D naught and H check A of D naught is reflexive. And restricts to L2 ME pairing. Okay. So actually I lied, we're not gonna prove it that way, we're gonna prove it slightly differently. So if now we have, so that's an alternative proof. Forgetting my own proof here. So if if we prove this to be an isomorphism, so D naught to A tilde D naught perf is an iso, then clearly this is a perfect pairing. Okay, so we prove that it's an iso. So how do we do that? So fix. So we prove is an iso. And restricts to the L2 pairing, i.e. the restriction of this perfect paired compactly supported or to smooth functions is the L2 inner product. Okay, so how do we prove that this is an iso? So we're going to prove two estimates. So first of all, let's take this U in the space H check A tilde of D naught. So what do we know from last time? So from the last lemma, we can rewrite this. Okay, so I should say that if we, okay, let me take some. So let U be in C infinity partial M E. Clearly, we have that, I mean, this object is smooth, right? So we clearly have this in C infinity partial M of F. And what else do we have? So we also have that, okay, so I'll say that in a second. So we now estimate this. So we can estimate this. So remember from last time, we can extend. So we have this following estimate. So this is the lemma. So sorry, this is E star. So we're applying the lemma here to the operator D formal adjoint, right? So what's this? This is equal, so this is going to be equal to or equivalent, sorry, there's squares here. So this is equal to d perp sigma naught inverse star E star of U squared. And this is L2 on the cylinder plus now inverse star E star of U L2 on the cylinder. Okay, so what is this now? So this is equal to negative, so as we wrote before, this is negative sigma naught dt negative sigma naught inverse star a star sigma naught sorry, so there's a sigma naught here, star sigma naught inverse star E star of U L2 Z squared plus this lower order term, of course. And so the point is that things cancel here now in this expression. So what are we left with? Well, we're left with, so the first expression, it's readily verified. It simplifies to sigma naught inverse D star. So that's the graph norm squared plus now we have, okay, so it's the graph norm. So I'm absorbing both terms into here. And this, as we recall, is bounded by the H hat A D naught norm. Okay, so what we've proved is one inequality. So for the opposite inequality, so we use E tilde of U equal to e to the minus t modulus A tilde of U. So this is the extension operator with respect to the D so this is extension operator for the formal adjoint, and so by symmetry obtain sigma naught star of V H hat A of D naught is bounded now by sigma naught star E tilde of V inverse D naught star, which is going to be bounded now by V in the H A nope, this is H A tilde check D naught. Okay, so this shows that we have the right estimates on so we see here that we have the required estimate on a dense subspace. So it's an invertible map on a dense subspace with the right estimate. So so we have that this partial M E to partial M F. This is a bijection with estimate sigma naught inverse star of U H A D naught is equivalent to U H check A tilde of D naught. Do I have this the right way around? No, I don't have it. This is the hat. So this is the tilde of D naught perp, and okay, this is the D naught perp, sorry, and this is the hat. um, hat of A. Right. And by density asserted, so by density conclusion follows. Okay, so I mean, okay, so we've proved something here, but what have we really obtained, right? So the point is, so what have we really done here? So what have we achieved? So we have D naught on, so this is an operator on E. And we have D naught perp on F. So on E, so maybe I'll just write this down. So we have a space H check A of D naught that describes the maximal domain. And here we have a H check A tilde of D naught perp, which describes the maximal domain of the formal adjoint. I don't know why I decided this tabular format. Maybe that's a bit of a silly thing to do. But we also have here this space, which is, of course, isomorphic to the adjoint, or the dual space of this space, right? So what have we achieved here? What we've achieved here is we've shown, so all of these are, so this is, maybe I should write on E, right? So these are spaces on E, and these are spaces on F. So what have we done here? So what we've done is, maybe I'll write this to the left here. So, so I'll write that this A D naught is isomorphic to the hat space. And what we're saying now is that actually this hat space is isomorphic to this space here. So by symmetry, of course, we can have a corresponding a hat space here with respect to this operator, and this will be isomorphic now. So these two spaces will also be isomorphic, right? We can just run the symmetric argument. So the point here is that a priori, if we look at boundary value problems, so we look at some boundary conditions and we get some operator here on E, and then we look at the adjoint operator and we get some information here, or an operator on F. But if these two spaces are isomorphic, then it means that we can describe everything in terms of just spaces on E. Okay, so if B H check of D naught is a boundary condition, and B perp is the corresponding adjoint condition for F, then B perp is a space in this A tilde of D perp naught, and so now this is equivalent, and now this is of course a bundle over F, or this is a function space over F, right? But by this proposition, we can equivalently consider so the question is, how do we get the corresponding condition? So we've already looked at that, right? The corresponding condition is, so maybe I'll write this the other way so we can write the corresponding condition, just to recall what it is. So what's the corresponding boundary condition? Well, this is where we take V restricted to the boundary such that V is in domain of DB adjoint. Okay, so DB adjoint, so the adjoint of DB is going to be, so this is of course an operator, so this is contained in DOM D max, 0 max. I should really write zeros everywhere here, I'm sorry. Right? So the point is that we know what this is, right? But we know this by first going into, by taking the interior adjoint and then restricting. But by this proposition, we can equally consider the space, say, so I can instead equivalently consider the space sigma naught star B perp, which is now because we've proved that this is an isomorphism now between these two spaces. It's a Banach space isomorphism. This is now a subspace of D naught, right? But now everything here is on the bundle E. We don't need to actually consider two separate bundles. We can understand the operator and the adjoint. So we can understand boundary conditions for the operator and the adjoint boundary conditions only by considering subspaces of E. Okay? So let's strengthen this a bit further, right? So let me further sort of talk about. Let's refine this a little bit more, right? So let's prove this lemma. So this lemma says that this map. So let's understand this a little bit more. So a priori, the isomorphism tells us that we can pull things back nicely, but let's also really see how this interfaces, because we have spectral cuts with respect to this A tilde. So the A tilde, here all of the A's that we're choosing are invertible operators. So the A tilde will also be an invertible omega bisectorial operator. And this is the adapted operator for the D naught for the formal adjoint. So again, we have a description of this space. So let me just quickly write this space. So this space is chi minus A H a half F plus chi plus of A tilde minus a half on F. Right, so we want to now understand how this isomorphism moves these spectral cuts between A and A and this A tilde. So the lemma says this. So if we take these spectral cuts, so remember, so let's just recall before we move on for this lemma. So recall that the hat space is at the level of the adjoint operator, right? So this is the chi minus of A star acting on H now minus a half at the level of the adjoint, right? Because remember the way that the annihilator behaves, this pairing behaves with respect to the check and the hat spaces. So this is ME plus chi plus A star H half ME. Okay, so the negative and the positive gets flipped around for this dual space, as you would expect. So what does this do? So this map takes the adjoint spaces H plus minus a half on the boundary, respectively to minus plus A tilde H plus minus a half. So the plus goes to the minus, yes, that's the correct plus minus a half f. Okay, and that's what you would expect, because if we look at the spectral decomposition of the check space of the A tilde, so of course the negative h half piece is with respect to the positive projection. So at the level of the dual space here, it's the negative projection. So in order for things to match up, you would expect the negative piece gets moved to the positive piece, right? So how do we see this? This is just actually a simple calculation. So let's look at what the spectral projectors are, right? So, okay, minus plus A tilde. So remember what the A tilde was. The A tilde was negative inverse star A adjoint sigma naught star. But remember that we had a lemma before that said that when we have a conjugation of an operator, the spectrum remains fixed. Okay? So this is in particular equal to chi minus plus of, so sigma naught inverse star chi minus plus minus A star sigma naught star. So this is I should say zeta minus okay, so I think zeta minus u inverse t of u inverse is equal to u zeta minus t u inverse. All right, so this is something we mentioned very early on. And now the point is that we have a negative here. And the way that the negative of, so it's easy to see that the chi minus of negative A is the same thing as chi plus of A star. Well, chi minus of negative A star is the same thing as chi plus of A star. Okay, so that's the proof. And so why does the claim follow? Well, this is an operator that preserves Sobolev scales, right? It maps H alpha to H alpha, and therefore this gets absorbed. I mean, when we make this estimate, we can just, it's an invertible map, so everything behaves nicely. You know, when we take a section of some H alpha, we can always write it as the composition of this and the minus composition of that, and then we use this operator to move it to the other side. Okay. So that gives us some nice information on how this isomorphism moves the hat space to the check space of the A tilde for the adapted operator of the formal adjoint. Okay, so lastly, let me just give the integration by parts formula. So proposition. So this is the first integration by parts. So when we have dom d0 max, and we have v in dom d dagger 0 max, then what do we have? Then we have that d max, d0 max uv L2 mf, or zf I should say, minus u d max v So this is equal to negative u restricted to the boundary star v, and this is what? This is the pairing h check a d cross now h hat, so a naught here, a naught d naught. Okay, so this is the pairing. So the map sigma naught star maps something in the hat space of the a tilde to, the check space of the a tilde to the hat space of the a isomorphically. So what's the proof? Well, for u v in dom d naught for u in c infinity c of partial me and v in partial mf have Green's formula, and then the right hand side is equal to sigma naught. Okay, sorry, there's a restriction here. There's a restriction here. Sigma naught star v restricted to m L2, right, of E. Then by density of C infinity C in dom D naught max dom D naught max, and since the pairing beta of UV is equal to U, okay, I should write XY is XY L2, okay, so this is equal to X sigma naught star L2 ME from previous proposition, conclusion follows. Okay, so we're just piecing together all the things that we have together. Okay. So from what all, so putting all of this together, we can now really describe what the adjoint boundary condition is, right? So before I wrote down in a hand wavy way what it is, but what is really the adjoint boundary condition, right? So for B in H check of D naught, boundary condition, i.e. a closed subspace, the adjoint boundary condition B dagger, which we wrote before, is precisely B dagger equals sigma naught star, sorry, there's an inverse here, inverse star of B now annihilated with respect to this pairing, A D naught and H hat A D naught. Okay, so this is the proof is this is a straightforward computation. So I just want to really emphasize again that we have reduced the study of so what we have before. So let me just say this again, right? So so far we have that dom d naught max mod our dom d naught min is Banach space isomorphic to this space A D naught. And the claim is, and dom D naught max mod our dom D naught perp max is Banach space isomorphic to A tilde of D naught. But the claim is, but we have shown that, so I should say 1 and 2, both 1 and 2 can be understood from A alone, i.e. from, sorry, it's min, yes, D naught and H hat A of D naught. So, of course, the second space is the adjoint of A, but doesn't matter. I mean, the adjoint is now, I mean, A determines the adjoint, right? So we don't have to look at two separate bundles and two separate problems, everything. So, I mean, this is really saying that all extensions of D naught min sitting in D naught max and all extensions of D naught dagger min sitting in D naught dagger max, all of this can be understood simply in terms of this adapted operator on the boundary. Okay, so that's really going far with the goal that we had of really understanding these operators from an object that's just sitting on the boundary. Okay, so let's just sort of leave that there. Later on, we want to really get back to the general operators, and we'll talk about how to do that. So also all of the stuff that we've talked about now can also be talked about for a general adapted boundary operator by passing to, so I should maybe say that, remark by previous corollary, all of our considerations hold for any adapted boundary op by passing to AR, where R is a spectral cut. Okay, so all of the things that we did can really be understood in terms of that. So this is somehow a baby case of perturbing from one operator to another, which might not be equal on a neighborhood of the boundary, because the perturbation is very simple, right? The perturbation is just adding a constant, and that gets absorbed in the zeroth order terms of the operator. Okay, so, right. So before we can now start to consider the general operators, we have to talk about, again, a slightly more abstract concept. And that is the concept of maximal regularity. And so the idea is we want to also understand how this model operator moves Sobolev spaces. We want to understand, so we've described dom d max and dom d min, but in what's to come later, we want to really understand these operators in terms of we want to understand how they relate to the classic Sobolev scales and to also the local Sobolev scales, which are independent of metrics. So in order to have a conversation about all of those sort of things, we need to understand a concept called maximal regularity. Okay, so we're back into the general setting. So let the abstract setting, A and B be an interval and B a Banach space. And let LP of A be landing us in the Banach space B denote F on the interval A to B into B such that integral A to B of F T of B to the P to be finite. Okay, so these are Banach valued LP spaces. Okay, so maybe we'll restrict our conversation to Hilbert spaces because I don't think we need to go and look at this in Banach spaces. So let me give you the theorem. Of course, we won't prove this, but we need this theorem. This is very important. So this is L2 maximal regularity. So the theorem says, so this is this is really, so theorem 2.1 in Giga and so on. Well, okay, I'll put the reference in the notes. Let T be an injective, not even an invertible, injective, densely defined omega sectorial operator for omega in the range 0 to pi on 2 on a Hilbert space H. Okay. Suppose T enjoys an H infinity functional calculus. Let tau be some finite number, or actually non-zero number. It can be infinite, sorry. Then for every f in L2 0 to tau, landing us in H, there exists a unique solution to the following equation. So this is a Banach valued Cauchy problem, inhomogeneous Cauchy problem. dTu plus Tu is equal to F and U0 is equal to 0. So this is for, so this, the first thing holds almost everywhere T in the interval 0 to tau. And what does this solution satisfy? So there exists a unique solution to this, satisfying the following. So the first is that we need U to be in L2 0 up to T0 inclusive, and it's in the domain of the operator T for all tau naught that's less than or equal to tau and finite. This is the finiteness that I tried to jump the gun on before. Okay? So I'll explain this in a second because it's a bit technical and it seems a bit roundabout. So partial T of U is in L2 of 0 to tau inclusive h so this is for tau finite, or L2 0 tau h for tau is infinite. And the third point is the most important point here. There exists some constant, CMR, which depends on the angle of sectoriality, the H infinity constant, maybe the Banach space, all of which is finite. But the main important thing is that this is independent of tau and f, such that the integral 0 to tau dtu tau squared h dt plus 0 to tau tut squared h dt is less than or equal to CMR 0 to tau f of t h squared dt. Okay, and what is this solution? So this solution is generated as follows. The solution is generated by, so there's a solution generator, so this is a map 0 tau inclusive cross L2 0 tau h to L2 0. Now we have the T naught here again, right? So dom T. And how is it given? It's given by UT is equal to WTF, and this is the integral 0 to T of e to the minus t minus s. So it, again, heat equation f of s ds. Okay, so that's quite a lot to take in. So let's just understand what it means in words. So we have something like an inhomogeneous heat equation here. Okay, so if f was 0, we would have the heat equation. But of course, for the heat equation, the interesting thing is that we have non-trivial data on the boundary, right? On the non-trivial initial data. So this is an inhomogeneous equation with trivial initial data. The point here is that actually the partial t of u and the t of u, these are really guaranteed to be in 0 to t, 0 to tau, even if tau is infinite. But what cannot be guaranteed is that u is the u ends up in the domain of t. Sorry, let me start again. So we have that partial t of u, and so we obtain these solutions. So these solutions are really in a Locke sense, right? These are really solutions in a Locke sense. But if the tau is infinite, for instance, we will not be able to guarantee that u of that the u, the solution that we get, is going to land us in dom t all the way up to infinity. right? So it's only going to guarantee that we are landing in the domain of T on a finite cylinder, right? That's what the first condition says. But the partial T of U is fine, right? The partial T of U will actually exist on the infinite cylinder. But the point here is that the constants that we're getting really is independent of the tau and the F. So it's really on the infinite cylinder. Okay, so that's, so the independence of the tau here really comes down to the fact that this is really a constant that we get on the infinite cylinder, regardless of the problem. So, and the independence of this constant, for a fixed tau naught will really become of importance in time. Okay. So let me see here. So, sorry, I should really say this is independent of the tau naught. Sorry again, tau naught. Because we're really integrating this up to tau naught. Okay. Okay, so I said a number of things here, but maybe let me just write those things down so they're written down. So remark 1, tau equals infinity. We do not, in general, get that U is in L2 0 to infinity dom T. Okay. So the failure here is that U in L2 0 to infinity in H is generally not true. And remember here that Banach space dom T is the graph norm, right? So we need also U to be in L2 of H. But read off from estimate 3 that if T is invertible, then we have everything that we want, right? Then we have U in L2 0 to infinity H. Okay. So the second thing I want to say is that even though this looks very much like, and this is just a side remark, although this looks very much like a heat equation, actually there is an underlying wave phenomena here, right? So this is really a side remark for those of you that are maybe interested. So underlying all of this is actually a wave equation, or generator, I should say. What do I mean by that? i.e., in a Hilbert space, T having a H infinity functional calculus is equivalent to saying that the complex powers of T, so we can also form complex powers of T, is bounded by some k e to the e to the theta modulus s. for all s, and for some k and theta. So this latter property. So this latter property, the latter property is termed bounded imaginary powers, or BIP. And so under the right conditions, TIS is really what? This is really e to the logarithm of the operator TIS, right? And this is the theta is some number. So there is a k and a theta. So whenever there's nothing written here and it's in an estimate, then it has to be existentially quantified, right? Absolutely, that's always how estimates should be read. Whenever there's an estimate and someone says blah 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 less than constant against something for all something, then I mean it's trivial, right? You always can, if you interchange the order of quantification, it's always true. So the quantification for it to be non-trivial can only be read in one way. There exists a kappa and theta such that for all s this is true. So this is a generator for solutions to the wave equation, partial t of u plus I logarithm t now of u equals 0. Imaginary powers. Oops. Oh, I don't know why I can't write today. Imaginary powers. So in general, i.e. Banach space, H infinity functional calculus implies bounded imaginary powers, but equivalence is only in Hilbert spaces. Okay, so that's just really a side remark. But for all this maximal regularity stuff, you don't need a full H infinity functional calculus. What you really need are bounded imaginary powers, right? But we cannot dispense with the H infinity functional calculus and try and assume something weaker if we're maybe trying to do this in a Banach space, because as we saw before, you know, we still need the H infinity functional calculus for the fundamental estimates that we have going from the maximal domain to the check space. So with all of this, having said all of this, now we consider the finite cylinder, right? So given all of this, consider now the finite cylinder. I.e. for some rho in 0 to infinity, Z rho is 0. Okay, so I have to be careful with what I do here. So before, I think we had the rho to not include so before we didn't include the endpoint, but now I want to include the endpoint. So what can we call this? Well, maybe just Z closed. bit annoying to have to carry that closed around, so maybe we can put the closed on the row. Yes, sorry, I should have thought about how to do that. So the point here is, here we have introduced a false boundary. So this is just a technical necessity, okay? So in application, this really has no consequence. So what is the false boundary? It's the boundary at the endpoint rho cross partial m. In application, we use eta equal to 1 in, say, 0 to eta equals 1 in 0 to, say, half rho, and eta equals 0 from 3/4 rho, say, to infinity. And given u in DOM d naught max, analyze eta u, because these two things have the same trace, since u restricted to the boundary is the same thing as eta u restricted to the boundary, which is eta 0, u0 in this notation. So this is u0. So the point is that at the false endpoint, so if I now look at eta u at the endpoint rho, this is equal to 0, right? So the false boundary disappears, right? It just appears as a technical necessity. So now in the analysis, so we set, so from here on, for A, which is invertible omega bisectorial adapted boundary operator, we set t equal to modulus A, which has a h infinity functional calculus, t naught equals to this rho, t tau equals to infinity, and h is now going to be L2 of z rho e. Okay. Now let's define the following very important operator. So we define an operator S naught. I won't worry about the mapping properties of it yet. So S naught of u of t is defined to be what? So this is defined to be 0 to t e to the minus t minus s modulus a chi plus of a u s ds minus t to rho. So I should say here that rho is to be chosen later, right? So this is to be chosen later. But the point is that we just fix some rho now for the moment, right? We don't care what it is. Okay. So e to the minus s minus t modulus a chi minus a u s ds. Okay. And also let's define C rho of us is what? This is u of rho minus s. Okay, so I think we have time to write out this next important lemma and its proof. It's very short. Lemma. So the following hold. So 1. S naught u of t is equal to, so W here is the generator. Okay, so this is the generator of solutions of the initial of the inhomogeneous part chi plus of a. So this is clear, minus, now this is going to be rho minus t of chi minus of a of C rho applied to u. Okay, so I mean it's obvious that that's true, but let's just really write it. The second thing, chi plus of a of s naught of u at 0 is equal to 0, and chi minus of a s naught of u at rho equals 0. Okay, so this is by design, in fact. And the third and very important point is this: sigma naught inverse d naught of s naught, which is equal to partial t plus a acting on s naught, is the identity. Okay, so it's a left inverse to d in some, yeah, up to this sigma naught term. Okay, so what is the proof here? So for 1, apply coordinate transform s maps to rho minus s in the second term of definition, and 1 pops out. Okay. The second thing, for this, all that is really required is that the functional calculus self-commutes, right? Because the functional calculus is going to commute with the resolvent, and then, of course, the spectral projectors commute with resolvents, and therefore, the second point is true. The third point, okay, so what is the third point? So write u equals to u plus plus u minus, where u plus minus is chi plus minus of a of u. Functional calculus. So it suffices to show that partial t plus a of s naught u plus minus is equal to u plus minus. So using the fact that modulus a is equal to a signum of a, we have dt s naught u plus is equal to negative a signum a s naught u plus plus u plus. And so u plus we wrote as chi plus of a of u, which implies that signum of a u plus is equal to u plus. Sorry, there shouldn't be a u here. Hang on. No, there should be. Sorry. And therefore, partial t plus a of s naught of u plus is equal to u plus. Right? We're just taking this side over to the other side. And for u minus, we'll leave it very conveniently as an exercise. Right? But it's not any more different. Okay, so of course it's not going to be a right inverse, and that's what we will start investigating the next time round. Right, well, yeah. First we can explore the mapping properties of this S naught, and then we'll start thinking about the right inverse properties of S naught. Okay, I'll leave it at that. Thank you very much. Any questions? No questions. Okay. So, see you next time.